we know that Hermitian operators and their eigenfunctions are very important in quantum mechanics. So let's look at that in the context of Dirac notation. And what I can do is really illustrate some of the efficiencies that now that the Dirac notation gives us in some of these problems by essentially proving theorems that we've already done, but I'll do it now using Dirac notation. And the first one is one that you should have recall. And we'd shown earlier that the eigenvalues of a Hermitian operator are real numbers. And remember, that is very important because we know that when we make measurements in quantum mechanics, what's the return in a measurement of a quantum system is an eigenvalue. And we deal with real entities. We deal with masses, which is a real number, or energies, which is real numbers, etc. So that's the requirement, really a requirement of the theory of quantum mechanics, that any physical quantity needs to be represented by a Hermitian matrix so that its eigenvalues are real. And that comes from a basic theorem that Hermitian operators' eigenvalues all are real numbers. And so let's take a look at that. Here I've got a Hermitian operator. I used A because it could be any. And it's just a Hermitian operator. And remember what Hermitian is. It's that the Hermitian adjoint is equal to the matrix, or to the operator itself. And so I take the adjoint, or the conjugate operator, sometimes called, to A. And if I do that, and I find that that's is the same as the original operator, then I've got a Hermitian operator. And now then I'm going to apply that to a vector, and it's not any vector, but it's a very special vector, because when I apply it to this vector, this ket vector A, what it gives me is the same ket vector that I started with, and then in front here I get a constant called the eigenvalue. And so when you can find a vector that satisfies this, that when I operate on it, on that vector, it gives me the same vector back again with maybe a multiple multiplicative factor, then I found an eigenstate of this operator. The eigenvalue is this piece out here. It's just a number. And here, this is an eigenstate or an eigenfunction in our notation. Well, I can take the adjoint of this equation 1 pretty easily, and I know how to do that. It's simply, really you write these in reverse order. So A comes first, but instead of being a ket, it's a bra, and then you have the Hermitian conjugate of A, and that was one of the identities that I think I threw up. I can do that take the Hermitian conjugate of both sides of this equation 1. On this side, I get this term, and then when I take it over here, well, I get a ket vector. It becomes a bra vector, and then this number here at this point, I'll just represent that as a star. It's a number, and in general, taking the Hermitian conjugate of both sides, I have to complex conjugate everything and then transpose, and that gives me the complex conjugate of A here for equation 2. I can also, if you like, I can take a bra vector and operate on this side of this whole equation 1, and that's what I did to get the equation 3 here. Equation 3, I simply operated on this, or not operate, but took a inner product of A with this. This is simply another ket vector, and so I take its inner product with itself over here with A, and I do it over here as well. But A inner product with itself is some number. This piece here is just a number, so it comes out. And so from equation 1, operating taking the inner product with A, I get this expression 3. On the other hand, I can do the same thing up here with 2, except now I come in from the right side with a ket A. So operating on this side, or taking inner product of this side with A, I get A dagger. That's just a bra vector, and I can take an inner product of that with another vector A. And I do the same thing on this side. The A star, that's just a number. That came out of the eigenvalue here. And so I can pull that outside, which I do here, and then I've got A inner product A. And then finally on 4, we're considering only that the operator, this any operator, is any Hermitian operator, and so I know that A dagger is equal to A. And so 4, I can represent, just replace the A dagger by A, since it's Hermitian. And now then, if you compare equation 3 and equation 5, they're both, the left-hand side is the same on both of them. The right-hand side, though, from doing those two routes, I get a slightly different expression. I get A and an A star here. So from 3 and 5, they're both equal to the same thing, and so that says the right-hand side of one has to be equal to the right-hand side of the other. And that gets me just this expression. A times the inner product of A with itself, A star times the inner product of, that's this side here. See if I can get both of those in at the same time. Yeah, I think I can. A dagger A. So this side is this, and it's got to be equal to this side, which is this, and then the two inner products of the eigenstate with itself, those are going to be the complex number with the same complex number, so I can divide those out, and then I find that that A has got to be equal to the complex conjugate of A. So these are the eigenvalues. A has to be equal to the eigenvalues of the complex conjugate. And so that only occurs if you write this one as x plus iy, and this one the complex conjugate of that only occurs if y is 0. And so there's no 0 here, and so A is real. Oh, another one that's, I don't know if we proved this one, but eigenvalues of a Hermitian operator with distinct eigenfunctions of a Hermitian operator with distinct, i.e. different eigenvalues, are always orthogonal. And we do a kind of a similar thing here. Again, I've got a Hermitian operator. I operate with A onto an eigenstate, A1, and that gives me the state back again with its eigenvalue, the number multiplying. And I do the same thing on a different eigenvalue, or eigenstate, A2, that's associated with the eigenvalue A2. And we write it in this form. We're given that the two eigenvalues that we got here are not the same. They're distinct. So I have different values for the eigenvalue up here, A1, and the eigenvalue here, A2. And of course, we're still dealing with a Hamiltonian, a Hermitian operator A. It could be any operator, it doesn't have to be a Hamiltonian, but any operator. Well, from equation 1, I can take its inner product on both sides with A2. So I have an A2 and an A2 on this side. So one finds that this quantity, the operator A onto A1 gives me A1 back again. That's just a number now. It's an eigen value. I can pull it outside and I get A2 inner product with A1. So this quantity, again, uh, taking the inner product of all of both sides of equation 1 with A2. I can do a similar thing. Yeah, well, that leads me to this result. I can do a similar thing with the other one, but I don't really have to. What I would probably do is take the complex conjugate of this one. So now I'm going to take the complex conjugate here. And this one here. Complex conjugate of 2. Take the complex conjugate of both sides. And that simply changes this to a bra, and I get the complex Hermitian adjoint of A. On this side, I get, well, the complex conjugate of A2, but I know it's a Hermitian operator, A is, and so that's a real number. And the bra over here when I take the Hermitian conjugate. So take the Hermitian conjugate of that, I get this. And now then I can note that the Hermitian conjugate of this is the Hermitian conjugate of this operation. But this operator on A2 gives me the state times its eigenfunction back again, and then I can take the Hermitian conjugate of it to be this. It's just A2 times the bra. So the net result is this with A in between simply becomes A2 star. But again, A2 is a real eigenvalue. It was a Hermitian operator, and so the A2 star is the same as A2. And now that I can write both of those, on this one I operate from the left with A1, the other one I operate from the right. So A1 on this one up here, it all turns into this expression. And now then from 3 and 4, I get exactly the same thing in 4 here. A2 on the left-hand side. Let's go back up and look at 3. Same thing on the left-hand side, but I get a different expression on the right-hand side. In any event, this value A2, A1, this value A2, A1 is the same, and so the corresponding right-hand sides have to be equal. And so the right-hand side of 3 was this, the right-hand side of 4 was this, and they have to be the same. And this quantity is exactly identical, so I can bring it over to one side or the other. I think I took this one over to this side and factored that out. I have A2 minus A1. But A2 and my hypothesis and the theorem, they're different eigenvalues, and so this is not 0. And the only way that this equation can be true, and if this is not 0, I can divide it out, and that says that I have to have that this inner product between 1 and 2 is 0, which means that they're orthogonal. Now it turns out that one can prove a more general relationship, that if they happen to be the same value, then I've got a case of degeneracy. And at that point, you can always construct a linear combination in such a way that they are orthogonal. So even if they're equal, we can there's a way around it by constructing an orthogonal basis for that those degenerate states.